Solar storms. In 1859, an amateur astronomer named Richard Carrington climbed the stairs to his private observatory near London. He adjusted his telescope and projected an image of the sun onto a screen. He was looking at sunspots, areas of the sun that appear darker because they are slightly cooler than the surrounding areas. Suddenly, two patches of white light appeared around one sunspot. Before dawn the next day, spectacular displays of red, green, and purple light, known as auroras, lit up the skies as far south as Panama in Central America. In the eastern United States, people were able to read newspapers outside in the middle of the night. Further west in the Rocky Mountains, the light confused campers enough to get up and start cooking breakfast. Some people even thought their cities had caught fire. What Carrington had observed was a solar superstorm. A massive eruption on the surface of the sun sent billions of tons of electrical and magnetic matter hurtling through space. It even caused damage here on Earth. When the matter collided with our planet's magnetic field, it caused electrical currents to surge through telegraph lines, disrupting communication. No solar superstorm as powerful as the 1859 event has occurred since. That's why scientists find it difficult to calculate the impact a similar storm might have on today's more wired world. A hint came in 1989, when a solar storm a third less powerful than the Carrington event caused 6 million people in Canada to lose power. A Carrington-class storm could leave millions without light, drinking water, sewage treatment, heating, air conditioning, fuel, and telephone service for months. Few objects seem as familiar as the sun. There it is, up in the sky every sunny day. Yet few objects are so strange. Look through a solar telescope, and the sun is transformed. Streams of light the size of planets rise into black space, only to come back down hours or days later, as if controlled by some unseen force. Neither solid, liquid, or gas, the sun is made up of plasma, the fourth state of matter. Scientists are learning more about the sun and how solar storms form. The sun is packed with magnetic fields, some emerging on the surface as sunspots. They help to power the solar wind, sending a constant stream of particles out into the solar system. These fields can also become entangled with plasma, forming gigantic loops that are illuminated by the hot, glowing plasma. When loops cross, they cause the enormous plasma eruptions known as solar flares. Such flares release intense energy into space. The Carrington event consisted of a powerful solar flare that produced the second of a rare pair of plasma eruptions. The combined force of both eruptions squashed the area where the Earth's magnetic field interacts with the solar wind, down from its normal altitude of 65,000 kilometers to 6,500 kilometers. The matter entering the upper atmosphere set off intense auroras over much of the Earth. A Carrington-class superstorm probably occurs only once every several centuries. But even much smaller storms can cause considerable damage, especially as humans become increasingly dependent on technology deployed in space. Solar storms disrupt the ionosphere. This is the layer of Earth's atmosphere where auroras occur, 100 kilometers above the Earth's surface. The pilots of the nearly 11,000 flights flying over the Arctic each year rely on shortwave radio signals bouncing off the ionosphere to communicate in an area beyond the range of communication satellites orbiting over the equator. When space weather disrupts shortwave communications, planes flying these polar routes have to be diverted. This can cost as much as $100,000 a flight. GPS signals are also affected, resulting in positioning errors. This means that surveyors must pack up and go home. Floating oil drilling rigs have trouble remaining on station, and pilots cannot rely on GPS-based systems employed for landing at many airfields. Unlike satellites in space, most power grids have no built-in protection against a powerful solar storm. Since large transformers are grounded to the Earth, magnetic solar storms can produce currents that could cause them to overheat, catch fire, or explode. The damage could be catastrophic. A solar storm as strong as the 1859 event could damage the entire grid. Such a storm might send hundreds of millions of people back to an electric way of life for weeks or months. In 1859, the world had few tools for studying the sun. Today, scientists are able to use satellites to constantly monitor our home star. One pair takes 3D images revealing how plasma eruptions speed out through space. Another monitors the solar winds. Scientists cannot be sure of a storm's intensity until it reaches this satellite, sometimes a mere 20 minutes before it reaches Earth. Many researchers are therefore concentrating their efforts on forecasting a storm's potential strength and its likely arrival time, allowing vulnerable systems here on Earth time to prepare.
Starstruck. It's hard to be modest when you live in the Milky Way. Our galaxy is brighter and more massive than most other galaxies. From end to end, the disk-shaped Milky Way spans 120,000 light-years. Encircling it is another disk, composed mostly of hydrogen gas. And enclosing that is an enormous halo of dark matter. Indeed, our galaxy is so huge that dozens of lesser galaxies circle it, like moons orbiting a planet. Giant galaxies like the Milky Way and the nearby even larger Andromeda galaxy possess the power to create a rich supply of iron, oxygen, and other heavy elements, heavier than hydrogen and helium. Such heavy elements are the building blocks of planets and are essential for life. When a star explodes in a smaller galaxy, this raw material shoots out into space and is lost. But in the vast Milky Way, the elements encounter gas and dust along their path and are restrained by the strength of the galaxy's gravitational field. These impediments slow their speed, so they can enrich star-forming gas clouds with the ingredients for new generations of stars and planets. That's what happened 4.6 billion years ago, when the Sun and Earth were born. Because we reside within the Milky Way, we actually know less about its overall appearance than we do about distant galaxies. Think about it this way. In the absence of a mirror, you know more about your friends' faces than your own. Nevertheless, in the past decade, astronomers have made numerous startling discoveries about our galaxy, beginning with the revelation that a huge black hole lies at its heart. Every star in the Milky Way revolves around this black hole, named Sagittarius A star. The Sun, 27,000 light-years away, completes a revolution once every 230 million years. Within just a light year of the black hole, there are more than 100,000 other stars caught far more firmly in its grip. some take only a few years to complete their orbits. These paths reveal that Sagittarius A star is 4 million times the mass of the Sun. Every now and then, the black hole swallows a planet or star like a particularly voracious vacuum cleaner. The victim is heated to such high temperatures that it lets out an explosion of X-rays, which light up nearby gas clouds. This helps keep a record of the black hole's past feasts. For example, in 2004, scientists reported an X-ray echo in a gas cloud some 350 light-years from the black hole. Since X-rays travel at the speed of light, the echo indicates that an object fell into the black hole around 350 years ago. The X-ray intensity suggests it had the mass of a small planet. Surprisingly, the black hole also flings stars away. In 2005, astronomers reported a star racing away from the galactic center at 709 kilometers a second. At that speed, it will soon leave the galaxy. 15 more of these fast-moving stars have since been discovered. Over the Milky Way's lifetime, the black hole may have flung 1 million stars out of the galaxy. Despite the violence around the black hole, the galactic core is a fertile place. Stars congregate at the galaxy's center, so the life-giving heavy elements they create are most plentiful there. Even the newborn stars near our Sun, halfway between the black hole and the edge of the galaxy, possess orbiting disks of gas and dust that survive long enough to give birth to planets. In contrast, prospects for planets at the galaxy's edge are bleak. Over 100 newborn stars at the edge of the Milky Way were recently found to have low supplies of heavy elements. For example, their oxygen content was only 20% of the Sun's. Most of these young stars have already lost their planet-forming disks of gas and dust. No disks, no planets, no planets, no life. Stars with even lower amounts of oxygen and iron offer insight into the birth of the galaxy itself. Residing in the halo extending above and below the galaxy's disk, these stars are so ancient that they formed before earlier generations of stars had a chance to produce heavy elements. Astronomers date these stars, and hence the age of the entire galaxy, by studying globular clusters, tightly packed groupings of older stars. However, estimates of their ages depend on theories of how stars live and die. Fortunately, there is another way to measure the galaxy's age. In 2005, a German graduate student named Anna Frebel began looking for individual stars in the halo. She discovered one that was chemically primitive. It had relatively few elements, meaning it must have been born before many generations of stars had chemically enriched our galaxy. And this halo star contained elements that are far heavier than iron, including uranium. She measured the amount of uranium using a method similar to carbon dating and estimated the star's age at around 13.2 billion years old. That figure suggests that the Milky Way is only slightly younger than the universe itself, which is 13.7 billion years old. The mighty galaxy, whose countless stars would later make life possible on Earth, certainly didn't waste any time being born.